Hi, in this video I'll be explaining the efficiency of Carnot engine. I have already explained the Carnot engine itself in a previous video, and please do have a look at that. So let's start with the PV diagram. We have already seen that the four processes constitute a Carnot engine's working. The isothermal expansion of the piston, followed by the adiabatic expansion, and the piston starts moving back. You have an isothermal compression where the temperature remains constant and the piston moves back to its starting point, which is the adiabatic compression, where there is no heat transfer of the surroundings. In this video, we'll be looking at a new graph called the temperature-entropy graph. The graph actually is very simple, and I wish all graphs looked like this. So the isothermal expansion means constant temperature, so it's just a straight line. The red line is just straight. The adiabatic expansion, the blue line, is vertical line, and there is no change in entropy, so that's a straight line as well. The isothermal compression is another red line because the temperature is same, so it's a straight line, and the adiabatic compression is a vertical line too. So the temperature entropy diagram gives new insights to understand the Carnot cycle. Let's plug in the processes as we know them. The red line, the isothermal expansion. Then the blue line, the adiabatic expansion. Piston starts moving back, isothermal compression. And piston finally moves back to its starting point, which is the adiabatic compression. So the rectangle is complete. And on the x-axis you have the entropy changes. If you look at it another way, we lit the burner to give heat to the gas. So in the isothermal expansion, heat has been given to the gas. In the further expansion of the piston, which is the adiabatic expansion, there can't be any heat exchange, so there is no heat arrow there. When the piston starts moving back as an isothermal compression, the violet arrow shows that the gas is giving off heat to the surroundings. Heat removal. So this is the way to look at the whole Carnot cycle. If we put all the digits there into the graph, we have the T1 as the hot, the T2 as the cold temperature, AB, BC, CD, and DA as the names of the individual four processes that constitute the cyclic and reversible process that we are seeing here. The entropy changes are from S1 to S2. Let's look at the equation. So the change in entropy will happen when there is a heat input or output at a constant temperature. That's a definition of entropy. So on the isothermal expansion top yellow line, throughout the entire line, Q1 was the heat that we gave to the gas. So the change in entropy S2 minus S1 is Q1 by T1. In the bottom horizontal yellow line, which is the isothermal compression, the gas is giving heat to the surroundings. So the change in entropy there is Q2 by the temperature at which it's happening, which is T2. Here the entropy is decreasing. During the adiabatic expansion and the adiabatic compression, there is no heat by the very definition of adiabatic, so there can't be any change in entropy. Anyway, they are vertical lines in a graph. I hope that's clear. With that, we should simply equate the S2 minus S1s and multiply, divide, and take a ratio of Q2 by Q1 in terms of temperature. Finally, coming to the efficiency of the Carnot engine with which we started.